All right. Good morning, y'all. So, let's see. Why did I have this open? Oh, right. One thing I realized that I have not said at this point, some of you figured it out anyway, but I want to make sure to say it explicitly. If you would like to meet with me in office hours, so first of all, if my door is open and you walk by, like, you can come in anytime. But if you go on the course website, it's linked here, office hours. You can sign up for a time, so you can't sign up today, but so you can pick a day and sign up for a time, and it shows up on my calendar, etc. Come on in, Raiden, have a seat. Anyway, I don't think I said that before. If I did, whatever. I've said it twice. Always happy to meet with you. And remember also that coming to office, like setting up an office hours appointment and coming gets you an engagement point. So you need like a certain number of points to get a grade. So that's one way. If you are unsure about something or confused, or just if something I said in class, you're like, I know this is not on the homework, but I was curious about that thing you said. Tell me more about that. Always happy to. Or if you're just like, let's play Go. That's fine too. Alrighty. So we are talking about propositional logic, and we've whoops. Okay. So we've covered all the basic propositional logic connectives, and, or, not, implication, like if and only if. There's one other big part of propositional logic that we haven't talked about yet, that we're going to talk about on Wednesday, which is quantifiers like for all and exists. But we'll get to that. But today what I want to talk about is if you compare to like algebra that you learned in, whenever. There are operators like plus and times, and right, just like we have operators like and or and implies. But so far the way we've been reasoning about these things is making truth tables, right? And probably, maybe at some point when you were learning algebra, you did probably make tables of like, functions like inputs and outputs, right? But that's not how you solve equations. You're like, let me list all the possible values and like see which ones work, right? I mean, for one thing, there could be infinitely many values, but even if there were only finitely many, that would really suck, right? We don't do that to solve equations. You do algebra, right? You can like move things around, divide both sides, all those kinds of things. And so is there something similar we can do with propositional logic? And the answer is yes. And so I want to teach you some algebraic laws that we can use to manipulate propositional logic, just like you can manipulate equations, like algebraic equations, with numbers. And part of the goal is that we can actually we don't need truth tables anymore. We can just do algebra, which is much nicer, but we kind of needed the truth tables to kind of bootstrap our way into understanding these things. So, algebraic laws for propositional logic. I'm not going to tell you every single law you could possibly write down. I mean, there's others, but I'm going to show you a set that will be complete in the sense that anything you could want to reason about, you could derive using these laws. You could use these laws to derive additional laws, right? If you want. But this will be a good set to start with. And these are the ones that I kind of expect you to know. So before I start just listing laws, I want to talk about two important kind of organizing principles that are helpful mnemonics to help us remember the laws. Because if I just listed them all, there's a lot. And it would just be overwhelming if you're just like, all right, I just have to memorize this big list of things. But usually, if there's a bunch of stuff to memorize, if you kind of have some organizing principles, that helps a lot. You don't just have to memorize a whole bunch of different things. So, so two organizing principles. So, first of all, number one, most, I'll say equivalences, or I'll call them laws, whatever, have what I call an opposite world version. Where we switch and or, and we switch true, false. So if you recall, and or are kind of opposite to each other in this funny way, right? If you pass through this mirror where true becomes false and false becomes true, then at the same time, like and turns into or and vice versa, right? And is true when both things are true, and or is false when both things are false, right? And so they kind of, and so basically anything that's true about and, if you flip it to or and flip every true to false, that's also going to be true about or. And so every time we have a law that says something about and, then we can like flip it and get another law that says something similar about or. And we'll see that. And so that means like basically you have half the amount of stuff to memorize, because if you know one thing about and or about or, like you know the other corresponding one. Okay. And number two, we can get, and actually someone brought this up the other day, I forget who it was, about thinking about like false being 0 and true being 1. And we can get some intuition by thinking in terms of I'll say 0, 1. So in particular, right, false is like 0, true is like 1, not is kind of like, I guess in that, it's like subtracting from 1. Right, like 1 minus 1 is 0, 1 minus 0 is 1, and so that flips it. And, what is and in this? Like if I think of false as 0 and true as 1, then what is and?
The addition?
It's not addition.
It's multiplication.
It is actually multiplication. Right, because think about it. So 1 times 1 is 1. True and true is true, right? False and anything is false. Right? If there's a false and you have an and, like that just makes the whole thing false. And that's just like what 0 does with multiplication. 0 times anything is 0. And so what is or? Or is kind of like what?
Plus or minus.
What was that?
Would be plus or minus, like.
What do you mean plus or minus?
Kind of how like you have in like a quadratic formula, plus or minus.
Well, plus or minus in that form, in that context, means it could be either one, kind of depending on. But yeah, I mean, but yeah. So or is kind of like addition. Not quite, right? Because like 1 plus 1 is 2, which we only have 0 and 1, so that doesn't really make sense. But you can kind of say, well, 1 plus 1, 2 is too big, so we'll just make it 1. And then it works, right? 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 0 is 0. So that's like false or false is false. But anything else, if you have a true, you add 1. So it's kind of like addition, right? But with a max of 1. So I emphasize again, this is definitely not the definition, and this is not really quite accurate. Like especially because the or doesn't quite correspond to addition, and so this gives us some helpful intuition. And there's some laws that we're like, oh, that looks kind of familiar from thinking about plus and times. But again, it's just like intuition to help us remember. But it's not. You can't rely on this to tell you exactly what it is. But again, it's a good start. Okay. So let's start listing some of the laws. So I'm gonna So I'm going to make a big table here. And it's going to be kind of wide, I guess. So I don't know. You can decide if you want to like turn your page, or if you're taking notes, or just make sure you have enough space. Each law will have a name, and then, you know, an equivalence. And then it's going to have an opposite world. Equivalence. I'm just going to okay. Let's start with, well, I don't know, let's see, how do I do this? Yeah, let's just do it this way. Let's start with some identity laws. And so thinking back to like 0 at 1, multiplication and addition, right? One kind of algebraic law that you're very used to is the fact that, for example, 0, if you do 0 plus something, it doesn't change, right? 0 plus a is always equal to a. Right, so 0 is the identity element for addition. And likewise, 1 is the identity element for multiplication. Right, you do 1 times something, 1 times a is a. And so we have the same thing that goes on here. And, you know, and again, if you think about, well, let's see, false is like 0. Well, let's do and. And is like multiplication. And like 1 is the identity for multiplication, so maybe true is the identity for and? Indeed, it is. So if we think about that, P and true, right? If P is true, then true and true is true. If P is false, false and true is false. So if you do something and true, then you just get whatever that something was. Right? So true is an identity element for and. So we'll say P and true is equivalent, logically equivalent to P. That make sense? Okay, what's the opposite world version? So remember, to get the opposite world version, we swap and or, and we swap true and false. And so the P I can leave alone, but if I swap the and to or and I swap the true to false, we should get something that also works. So this is saying false is the identity element for or. And again, if you want to convince yourself of that, you can think through the possibilities, make a little truth table, whatever, right? But since or needs one of its arguments to be true, right? Having something or false, like it doesn't really, not really telling you anything. So whatever this P is, that's going to be the result. If P is true, it makes the whole thing true. If P is false, then we just have 2 falses with an or. It's false. All right. What questions do you have so far? Making sense? So again, just like, you know, if you're doing some algebra and you see like, you know, x plus 0, you can just rewrite it and say, well, that equals x. Same thing here. If you ever are doing some propositional logic algebra and you see P and true, you're like, oh, that's just P. All right. Something similar, a little different, is we have some annihilation laws. What happens when you multiply by 0?
You get 0.
You just get 0, right? It doesn't matter what you multiply, it just kills it and you just get 0. Same thing happens here. If I do P and false, what am I going to get?
False.
It's just false, right? Doesn't matter what P is. And the opposite world version, P or true, it's just true. And this one, so this one has a nice, you know, if and is multiplication and false is 0, this is familiar. Something times 0 equals 0. Again, this doesn't really have a nice, like, adding 1 doesn't, I mean, I guess in this world where the max possible value is 1, right, adding 1 does destroy whatever, like annihilate whatever else you had. It's like it doesn't matter whether you start with 0 or 1, you add 1 to it, you're going to end it with 1. So in that sense, I guess it works, but a little less familiar. Okay. There's another kind of law called idempotence. This one does not have a corresponding thing with addition and multiplication. But if I do P and P, like doing and with P twice doesn't really tell us anything. It's just the same as P. Right? It's like it could be true and true, which is true, or it could be false and false, which is false. So this word idempotence has to do with an operation where if you kind of do it twice, it's the same as doing it once. Right? Or a binary operation where if you combine the same thing with itself, you just get that same thing. And so likewise, P or P is just equivalent to P. By the way, I'm not going to require you to memorize all these names. Again, it's one of those things where you may see these words, so it's kind of nice to be familiar with them, but I don't care whether you can, on a quiz regurgitate like which is the right name for these things. If you're just like, I know there's a law that says this, and I don't remember what that law is called, that's fine, right? Okay, what are some other laws, algebraic laws involving addition and multiplication that you know? And we can think whether those correspond to something here. Yeah, Spencer. Commutativity, right, where you can the order of arguments to plus and times doesn't matter. You can, a plus b is the same as b plus a, right? Wait, so do you think that's true for and or? Do the order of the arguments to and or matter or not? Yeah, they don't, right? They're totally symmetric. It just doesn't, and requires both things to be true. Doesn't matter what order they're in. Or requires at least one to be true. Doesn't matter. Yeah.
Distributive law.
Yeah, distributive also. Right. So let's write down commutativity, and then we'll do distributive next. So commutativity. So P and Q is equivalent to Q and P, and same thing, P or Q is equivalent to Q or P. Okay. So I'm going to put distributivity. There's one slightly simpler one that I want to do first before we get to distributivity. Other laws people know of? Yeah. Associativity, right. So that was the one that I was going to put here. So associativity. So associativity says, right, for example, if you have P and Q and R, where you sort of do the P and Q first, and then do and R, this is equivalent to P and Q and R. So let's think about why that's true. I mean, basically this is saying, the only way this is going to be true is if all three of these things are true. It doesn't really matter whether you first, check whether these are both true, and then, combine that with R, or do it in this other order. You're going to get the same answer no matter what. If all three are true, you're going to get true. If any one of those is false, you're going to get false. So it doesn't matter. So this means we can just write, if we have three things that we're anding together, we don't actually need to write the parentheses. We can just write P and Q and R with no parentheses, because the parentheses don't matter. However, if you have ands and ors mixed up, the parentheses matter a lot. Okay, so you can only leave out the parentheses if you've got all ands or all ors. But if you've got ands and ors combined, you definitely need the parentheses. And so, right, the opposite world version is just P or Q or R is equal to P or Q or R. Okay? So distributivity. What does distributivity say for addition and multiplication?
Whatever's outside of parentheses distributes out to whatever's inside of the parentheses. So
Yeah, so like give me an example.
So like 3, and then you have in the parentheses 2 times 1x, it would be 3, or the answer would be 6 times 3x, or 6 plus 3x.
Oh, okay, so if you had plus inside,
I might have said that
Okay,
wrong, but
okay,
you have
yeah.
a number outside of parentheses, you multiply
right,
it
like
by the
3
numbers
times,
inside.
you know, like x plus y or something, that would be like 3x plus 3y.
Yeah.
Yeah. Yeah, so in this case, like we say multiplication distributes over addition, right? And so what that would correspond to here is something like and distributing over or, P and Q or R would be equivalent to P and Q or P and R. That turns out to be true. I'm not gonna like prove it to you. Well, I can maybe think intuitively why that's true. Of course, we could make a truth table, and you would, if you did everything out, you would see like, yep, those 2 columns are exactly the same. So, by the way, if we wanted to make a truth table to check this, how many rows would it need?
You would only need 3, so, or in total if you're not involving any of the knots now.
No, we would need more than 4.
P.
We would need 8. Because I have 3 variables, P, Q, and R, and I need 1 row for every possible combination of values for P, Q, and R. And basically, every time we add 1 more variable, we're multiplying the possibilities by 2, because every possibility that we had before, we now have 1 where that one is true, and then 1 where that one is false. And so maybe we'll do an example of that a little bit later, but anyway, I'm not going to go through this in detail right now, but I would encourage you, if you like, later go and either make a truth table for this, or kind of try to think through what this means and convince yourself that this is always true, that this always works. Okay, but here's the funny thing. In algebra, right, so we said like multiplication distributes over addition. So if I do like 3 times x plus y, right, we get 3x plus 3y. Does addition distribute over multiplication? So if I have 3 plus x times y, can I say that's equal to 3 plus x times 3 plus y? Does that work? No, definitely doesn't, right? So it's not, I mean, it might be equal for some specific values of x and y, but it's not true in general. So in when we're doing arithmetic, addition and multiplication there's this asymmetry there, right? They're different. They kind of play different roles. And so this is another place that this analogy kind of breaks down. But here in propositional logic, right, and or are completely symmetric. So we definitely and distributes over or. If that's true, there must be an opposite world version where we flip all the ands and ors, and that must be true as well. And so indeed, or distributes over and. P or Q and R, it turns out, is equivalent to P or Q and P or R. Which is nice because you don't have to remember which one it is that distributes over the other. Either one distributes over the other one. All right, let's go with that. Okay. We're not done. There are 2 laws that we refer to as De Morgan laws, named after Augustus De Morgan, who I don't remember if I talked about him. I don't think I did, but he was a mathematician in like the 18 somethings. He published a book called The Laws of Thought. And basically he was like, let's take the idea of things being true and false and logic and kind of do algebra to it. And basically like this is what he did, which is extremely influential. And we don't do things exactly the way that he wrote down in his book, but pretty close. And or maybe, I'm sorry, I'm getting things mixed up. The Laws of Thought was by George Boole. That's where the name Boolean comes from. De Morgan did other stuff with logic. I don't remember. Anyway. Yeah. Sorry, I got those confused. But go look it up and figure out who De Morgan was. All right. So here's the thing: not P and Q. All right. So see if we can figure this out. If I make a statement, if I make an AND statement, right? In what circumstances is my statement false?
When one of them is false.
What was that?
When one of them is false.
When one of them is false, exactly. And so that suggests the negation of an AND is equivalent to so that AND is false when one or the other, or both, of those individual things are false. Another way to think about this is not kind of distributes over AND, except you also have to flip the AND to an OR. Right? So you can distribute this not over the P and the Q, but at the same time you've got to flip. There's got to be an opposite world version too that says how not distributes over OR. And you can think about it again, right? When is it not the case that P or Q, right? P or Q is false when they are both false. And so this is equivalent to not P and not Q. Right, again, it's just the opposite world version of this where we flipped ands and ors to the opposite thing. You can also think of it as, right, not distributes over an or, but you just have to flip the or to an and. So in general, if you have a not applied to something, you can distribute apply to an and or an or. You can just distribute the not, and you just have to flip the and or to the other one. Okay, let's see, one more in our table. So P and not P. And we talked about these the other day, actually. I think someone gave these as examples. P and not P is equivalent to what? It's always false. And then P or not P is equivalent to true. And we call, well, this doesn't really have a name. I'd call this a law of contradiction. And this is called the law of excluded middle. For interesting historical reasons I don't want to go into right now. Basically, it's kind of saying there's no, like, something has to be either true or false. There's no middle thing that could be, so it excludes the possibility of a middle thing that's neither true nor false. Okay. What questions do you have? I promise we'll do some examples in just a minute. Yeah, Spencer.
Argue with or notation instead of using like the.
What was that? What about the?
negation. we're using bars for negation instead of the,
Yeah, so what's your question? Like,
can I use bars?
can you use that? Oh, sure, I don't care. Yeah, I mean, it's an issue of like, different notations tend to be used in sort of different subfields or different communities, right? The bar notation, like like writing a bar over something, that tends to be used a lot in like digital logic. So we are later going to use an over bar notation to talk about set complement. And so that's one reason that I'm using this notation and not the bars, because it could be a little bit confusing. But I mean, it's not necessary. It's not fundamentally. It's not ambiguous because it's always clear whether you're talking about sets or propositions. But anyway, yeah. Braden, do you have a question?
Yeah, I was going to talk about the 3-bar thing again. What was it supposed to mean?
What the
I was trying to learn that with the homework.
with a bar over something?
Yeah, the 3 bars.
The 3 bars. Oh, this no. Okay, that's not. This just means logical equivalence, right? It means that these two things always have the same truth value, no matter what. No matter what the values are of like p of any variables p, q, r.
So it's saying like for each variable, it's always going to remain, the result's going to remain the same on either side.
Right. Yep.
I mean, I had another one. It was about the quiz.
Okay. So there's like 3 other laws. I don't know if they're exactly kind of. Well, one counts as a law. Which don't have like opposite world versions, so I'll just say also. So there's a law called double negation elimination, which says that not P is logically equivalent to P. Okay. This is one we did the other day, so that P implies, we haven't said anything about implies yet, right? P implies Q is equivalent to not P or Q. So technically, if you want to show something about implication, it's enough to just turn it into this and manipulate it with using the laws we know for or and not and stuff, and then you can kind of maybe turn it back in implication. You can, in fact, like derive other laws that more directly work with implication, and you know, like what happens if you do, you know, an and implies something. Like, can you manipulate that in some way? Or, and there are some laws like that. I'll let you think about those if you would like. And then, I think I wrote this down the other day too, right? P if and only if Q is equivalent to P and Q, or sorry, P implies Q and Q implies P. So again, if you want, like if you do this, if you have an if and only if, you could turn it into this. And then if you also, you could then turn these implies into this. So you can always sort of encode everything in terms of and or not. Okay. Let's do an example. Actually, let's see. Yeah, okay. I'm gonna make one up because I don't. Let's say, you know, simplify. You know, not P implies, not Q, not Q or R and Q. I totally made that up. Let's just see how much we can simplify it, okay? And this is the kind of thing that's really useful to be able to do algebraically, right? Because you can imagine something like this coming up where you sort of like, either you figure out how to express some condition, but the way you figured out how to express it like is in some kind of complicated nested way, and you end up with some complicated expression, or I don't know, for whatever reason. And then, yeah, you could just like make a big truth table and then figure out a nicer way to write it. Or you could kind of think really hard about it and try to think of something that's equivalent. But if you can just manipulate it algebraically, that's really nice, because then you don't really have to think about it. You just apply the laws, right? So, I don't know, what law would you like to apply first? There's a bunch of different things we can do. There's no like right way to do it, but. What is it? Distributivity, you said? Oh, so you're seeing like, where are you seeing we could do distributivity?
Not Q or...
Like this part here?
Yep.
Okay, sure. So that's equivalent to not... Oh, and by the way, I'm going to do this. You do not have to do things this way, but I think this is a nice format, basically where you... Let me finish writing this and I'll say not. Okay, now we do distributivity, so it's not Q or R and not Q or Q. There. Where you basically like, you list some things step by step, and then between each pair of things you put a symbol that says how they're related, and then on the right side of that line you put, maybe in brackets or something, like an explanation of like why they're related in that way. And so in this case, I'm just going to have a chain of, this is equivalent to this, is equivalent to this, blah, blah, blah. But I can write down the reason for each. We're gonna see, I'm gonna use this notation a lot. And this is a really nice way to organize things. And it doesn't have to be equals. It could be like less than, or it could be implies, or it could be, right? Any kind of way that two things could be related. You could have a chain of them that kind of state each. Okay, so how can we simplify this more? What law can we use next, Jack?
Excluded middle.
Excluded middle, yes. So this, here we have not Q or Q, which we know is equivalent to true. Right, so I can rewrite this and say this is not, P implies not Q or R, and true. So this is excluded middle. And actually, just for fun to help, I'm gonna, and again, you don't have to do this, but I'm gonna like underline the part that we're applying that law to, just to make it more obvious kind of where we're using these laws. Okay. What now? Yeah, Spencer.
You get rid of the and T
The and T? Yeah, so what do you mean get rid of it?
because anything and true is just the thing.
Yeah, so this is true is the identity element for and, right? And so we can just get rid of it. So this is equivalent to, so this is, oh, I forgot that. So this is not, P implies not Q or R. Is that right? Yeah. Okay, now what? I see a couple things we could reasonably do at this point.
Do another distributive, and then distribute the not.
Yeah. So there's these special like distributive laws for not, they're called De Morgan laws, right? Where we can, yeah, it's fine if you don't remember the names, but we can distribute this not over this or. We just have to flip the or to an and at the same time, right? And so let's do that. So we can say this is equivalent to De Morgan. Not P implies not Q and not R. Yeah? Yeah, go ahead.
Would it be best to write not Q is just Q?
Well, yes, it is equivalent to Q. I did this on purpose to emphasize that, like, that is like a use of another law. Now, yes, absolutely. Could you just do them both in one step? Yes, for sure. I just wanted to be, like, write it out extremely carefully in this example. But yeah, if you're doing it and you're just like, oh, I'm distributing the not over that, and so like, oh, not Q, that's the same as Q, I'm just gonna write Q. Just like you might do a couple steps of algebra in your head when you're doing, that's fine. So let's do that. So this is double negation. Not P implies Q and not R. Okay. Now what?
Against the law to distribute the not on the very outside.
Hey, good thinking. However, so we have a not here on the outside, and you'd like to do some kind of De Morganish thing to like distribute it. But what's inside here is an implies. We only have laws that say how does not distribute over and or over or. Now, if you would like, it might be a nice exercise to like work out if I have not applied to an implication. Can I come up with a nice algebraic law that says what that does? But right now we don't have one, so we need to do something a little more fundamental. Yeah.
The not R, Q and not R is just a true statement now, so that can be
Why?
simplified down because not R is R still a false?
We don't know what
this
R is.
context?
R is just a variable,
Okay.
so we can't assume anything about whether R is true or false. Yeah, that's right.
Can you expand the arrow into
It implies,
P
yeah.
and Q?
Yeah, so we had this law here. It said P implies Q is equivalent to not P or Q. So we can always, if you have an implies and you need to like manipulate it somehow, one thing you can do is kind of turn it into that. And I'm pretty sure we did this law as an example last time. We like made a truth table for it to convince ourselves that was true. For some reason, this is probably one of the hardest ones to remember. I just see students I've seen in the past, students often get confused about like, is it or and, like which one has a not. It does matter, right? You can't say P or not Q, that's not the same thing. I don't know, so maybe just, you can hear me say that and be like, okay, I need to focus on memorizing that one because that one is sometimes a little tricky to memorize. So we can do implication. Not. Oops. Dang it. So it's going to be not P or Q and not R. Right. Not P or Q and not R. All right, now we can do a De Morgan thing and move this outer not. And maybe this time, maybe I will actually do in one step. I will just, as we distribute the not, we're going to get not P. I'll just write it as P. But I can even do here. I can say De Morgan and double negation. Like we're using both laws at once. So we'll get P, the or flips to an and then not Q and not R. We can do De Morgan again here. We have a not applied to an and. So that's equivalent to P and not Q or R. I guess again we're using De Morgan and double negation. Right, because technically it would have been not R, and I just turned it into R. And at this point, like, you could just leave it like this. You could also distribute the and over the or if you want. It kind of depends on, I would say this is probably the simplest. If you distribute it, it's going to get a little longer. But maybe if you think it's nicer to have it in the form of like something or something instead of something and something, you could. I'll say like optional distribute. Okay. Questions? I'll leave you with another, we don't have time to do it, but the other example that I had that we could have done, and you can try it on your own, is to say show P implies Q and P implies R is equivalent to P implies Q or R, or Q and R. So this maybe I should write the other way around, but this actually shows that implication kind of distributes over and, right? So if I have P implies Q and R, it's the same as P implies Q and P implies R. So once we know this, we could just you could use that as another law that you get to use if you want. But how would we show that in the first place? Of course, one way is we could make a truth table. But another way now is we can actually use some algebra, right? So you could expand out the implies in terms of not and or, and then use some distributed laws and whatever to kind of. So what I would do is start with one side, and then say that is equivalent to this, is equivalent to this, and try to get to the other one. And if you can get to the other one by a sequence of equivalences, then you've shown that those are equivalent, right? I'm going to let you do that on your own if you want. All right, see y'all on Wednesday.
I think